Hello, and thank you for joining Maplesoft's Virtual User Summit. My name is Shola Slough, Technical Communications Specialist at Maplesoft, and I'm your host for this presentation. The presenters for this session are available in the Communication Lounge from 2:30 to 3 p.m. for a live chat on the day of the event. So please head to the Communication Lounge and select the appropriate scheduled chat for this presentation to ask any questions you may have. If you are viewing a recording at any other time and have questions, please leave them on the message board in the Communication Lounge and a Maplesoft representative will get back to you. This session is titled, Tackling the Challenges of Engineering Research. Engineering researchers are making significant strides in their work with the help of advanced physical modeling technology. This presentation explores the work of three renowned researchers and discusses such diverse projects as space rovers, hockey sticks, parallel manipulators, and electric and hybrid electric vehicle batteries. Let me now introduce our presenters. Dr. John McPhee is a professor of systems design engineering at the University of Waterloo and NSERC Toyota Maplesoft Industrial Research Chair in Mathematics-Based Modeling and Design. Dr. McPhee's main area of research is multi-body system dynamics, with principal application to the analysis and design of vehicles, mechatronic devices, and biomechanical systems. He has won many awards, including the 2013 NSERC Synergy Award for Innovation, the Premier's Research Excellence Award, and the I.W. Smith Award from the Canadian Society of Mechanical Engineers. Dr. McPhee completed his term in 2009 as the Executive Director of the Waterloo Centre for Automotive Research, spending a sabbatical year at the Toyota Technical Center in Ann Arbor, Michigan. He holds a PhD in Mechanical Engineering from the University of Waterloo, Canada. The second presenter in this session, Dr. Venkat Krovi, is Professor of Mechanical and Aerospace Engineering at the State University of New York at Buffalo, as well as Director of the Automation, Robotics, and Mechatronics Laboratory. His research activities focus on the complete life cycle treatment, that is the design, modeling, analysis, control, implementation, and verification of a new generation of smart, embedded mechanical and mechatronic systems. Dr. Krovi is the conference chair of IDETC 2014 and the current associate editor for the IEEE's Transactions on Robotics. He has also served as technical editor for the IEEE and ASME Transactions on Mechatronics and as associate editor for the ASME Journal of Dynamic Systems and Control. The final presenter for this session, Dr. Amir Khajepour, is president of AEMK Systems and professor of Mechanical and Mechatronics Engineering at the University of Waterloo, as well as Canada Research Chair in Mechatronic Vehicle Systems. Dr. Khajepour is an authority in mechatronics and robotics. His research includes modeling and development of advanced systems for the automotive, space, and manufacturing industries.
Hello, everybody, and thank you for attending my webinar, my e-conference presentation. My name is John McPhee, and I'm an Industrial Research Chair at the University of Waterloo in Ontario, Canada. And today I'm going to talk about my use of MapleSim to support my engineering research. In my lab at the University of Waterloo, we mainly focus on dynamic modeling, simulation, design, and control of biomechatronic multi-body systems. And to be more precise, we're trying to answer questions like, how do systems move, how can we control them, and how can we better design them? And for these goals, we found that MapleSim is a very useful tool to support this research. Here's a quick outline of my presentation. I'm going to focus mostly on applications today. I'm going to start with our research on contact dynamic modeling. I'll then move on to some applications involving planetary rovers. Then I'm going to talk a little bit about biomechanics, biomechatronics, and sports engineering. And finally, I'll finish off with some research we've been doing with Toyota on the modeling of electric vehicles and hybrid electric vehicles. Our work on contact dynamics was initiated by a project that we began with the Canadian Space Agency. And on the left of my slide, you can see the SPDM, the Special Purpose Dexterous Manipulator, or Dexter for short. And it's used to remove objects from receptacles in the space station, such as this battery unit that's shown on the right-hand side. And what you notice here is that this maneuver involves contact between a couple of moving parts over a distributed surface. And so our goal was to create high-fidelity models of these contact dynamics that ran reasonably quickly. Now, when we looked at the literature, we found a couple of things. First of all, people were doing a lot of modeling using impulse momentum methods. This is an approach where you use a coefficient of restitution, and impact is assumed to occur with time basically frozen. This works very well in computer games where you're not so particular about the accuracy of the physics. In contrast, a continuous dynamic model would actually represent the contact force between the two bodies during the period in which they are in contact. Now, the most common approach is to assume contact at a point between two bodies and use something like a Hunt-Crossley model that is shown here, in which the contact force is some function of a depth of penetration between the two bodies. So the two bodies are assumed to interpenetrate, and that more or less gives you a nonlinear spring with some damping to force the bodies apart. And so in the bottom, I've shown a plot of what would happen if you drop the ball inside a cylinder using this Hunt-Crossley model. The ball will bounce and then roll without sliding forever, because once it starts rolling without slipping, there's nothing to dissipate energy. We wanted to model contact over distributed surfaces, so we looked at using a Winkler foundation model in which you had a distributed contact load over the whole surface. Well, it turns out that when you integrate that contact force over the surface, you now find out that your contact force depends upon the volume of interpenetration and not the depth of interpenetration. And there's a couple of other nice things that naturally arise out of this approach. For example, when you integrate those contact and friction forces over the surface, you naturally get a rolling resistance moment also appearing in your dynamic model. So if we drop the same ball inside the same cylinder, it now bounces, rolls, but then rolling resistance will eventually bring it to a stop, which clearly is a much more accurate representation. We've done a number of applications. On the left is a well-known tippy-top toy. I'll show you an animation of that in a second. On the right is a famous benchmark problem. It's called a peg in a hole, and it involves contact over surfaces with friction. It was relatively straightforward to implement our model inside of MapleSim. We did this using a custom component in which we could directly code our mathematical expressions. On the left is a representation of the two bodies in contact. On the right is the MapleSim implementation. And once we had done that, we could go back to that tippy top and we could simulate the response. And if you've ever played with one of these toys, you'll know that when you spin it, it actually flips over onto the peg until eventually you dissipate energy and it stops rolling. This is a very difficult system to simulate, which is why I'm showing it to you. We've done other applications as well. Here's an automotive clutch plate in which the two surfaces are sliding before they start rotating together. And later on, when I talk about biomechanics, I'll be using the same contact dynamic model to model human feet that are impacting the ground. And at the top is a schematic representation of some of the surfaces in contact with the ground. And we've validated our models against finite element models as well as experiments in our lab. Next project also involved the Canadian Space Agency, and this was when they started to investigate planetary rovers. Now on the left is the so-called Junior rover. It's a prototype of a future space mobile rover. And on the left, it's being tested on the big island of Hawaii. On the left is our MapleSim model. And what we've been able to do is capture the unique triple rocker design of this particular machine and see how it moves over rough surfaces. There's a rocker in the front, which connects two rockers on the two sides, and on the two side rockers, two wheels are mounted. And this arrangement allows any one wheel to move over a fairly large obstacle. This is a MapleSim representation, and on the lower right we have two tires. On the lower left we have two tires, and they both connect to those rockers on the side, which in turn connect to the main chassis through pin joints. There's a rocker at the front that allows wheels on one side to move up in the air relative to wheels on the other side. And this is best shown through a MapleSim simulation and animation, in which you can clearly see that we can accommodate any one wheel going over a large obstacle. We did some experiments on the actual vehicle in order to gather detailed data for model validation. The one thing about planetary rovers is that they don't move very fast, so the dynamics are not always that exciting. In this particular case, we had it going over a 3D surface made up of soft soil, as you might find on the Mars surface. We did a 3D LiDAR scan of that surface, and we developed special models for the tires interacting with soft soils, and that allowed us to create this MapleSim simulation of those experiments shown here. The 3D LiDAR scan was used to create the surface in MapleSim. We used our model with the specific tire-ground interface contact forces, and we were able to show very good agreement between our MapleSim simulation and our experimental results. Again, the dynamics are not very fast, and so it's not the most exciting maneuver to watch. I'll now move on to talk a little bit about some of our work in biomechanics and sports engineering. And in a lot of this work, we're trying to develop predictive models that will tell us how assistive devices or training devices will help the user. And so we're trying to do forward dynamics in which we specify forces on the system and we predict the motion. Now, this is in contrast to most approaches to biomechanics, which is to measure the motion ahead of time and work backwards to figure out what the forces are. That's fine to do, but it means you're always doing user testing, and you can't do truly predictive simulations. So we've used our MapleSim model, which is based upon a linear graph representation, if you look under the hood for the theory underneath. Maple symbolics that give us fast simulations, our previous contact dynamics models. We have a balance controller to make sure that our human walker doesn't fall over. And in order to create natural gaits, we're minimizing metabolic energy consumed during a gait cycle. And that's because experiments have shown that humans walk in such a way as to minimize their metabolic energy consumption. So to discover these natural gaits, we're using an optimization routine in which we call our MapleSim models over and over again many times. And that's one reason why we're using MapleSim in this work, because we require very fast models that simulate quickly because we need to run them over and over again. And what I just showed you was a simulation of a gait that was entirely discovered by an optimization algorithm that minimized metabolic energy. We've since added a detailed muscle model to our human walker, and that muscle model includes muscle activation and contraction dynamics. It includes muscles wrapping over surfaces as they pass across bones and joints. And again, it uses that previous volumetric model for foot contact. Now, we need to validate these models always to make sure that we're representing reality. And so in our lab, we have a number of useful tools for measuring ground reaction forces and human motions and we can go back and validate our models to make sure that they're representative of reality. Here's another project that we've been working on for quite a few years, and this is in the area of golf equipment design. Some of this work is being done with companies like About Golf and Cleveland Golf, as well as the magazine Golf Digest. And what we found is that golf equipment is becoming extremely good. In fact, it's somewhat reaching the design limits that are set by the United States Golf Association and the Royal and Ancient of St. Andrews. So now what companies are interested in is matching the equipment to the human. And that's where our detailed models of club and equipment come in. So in this particular MapleSim animation, we've represented the golf shaft by a flexible beam model from MapleSim, which allows us to model a varying stiffness all the way down the shaft. So the shaft might be stiffer at the top or stiffer at the bottom. It varies all the way down and can be tuned for different golfers. Now, the characteristics of the individual golfer are measured, and they are input as 6-degree of freedom motions at the grip. And the club itself has known mass and inertia properties that are entered into the MapleSim model. This is a project that we did for Cleveland Golf. And if you simulate and animate the response, you'll see all the characteristics of a normal swing, including the fact that the shaft is bending ahead at impact in order to launch the ball at a higher and farther trajectory. So we have very good agreement, again, between our MapleSim model and a number of experiments that we did to validate the model. Well, switching to perhaps a more Canadian sport of hockey, although I would add that Canada is the defending gold medalist in the sport of golf, which is returning to the Olympics in 2016. That's a little plug there for the Canadian Olympic team. In hockey, we see something that you don't see in golf, and that's equipment breakage. In particular, we see a lot of sticks, hockey sticks, being broken in the course of a game. And not only does this affect the team in a negative way during the actual play at the time, but it's a huge cost issue for the teams and the players. So in golf, we do a lot of robot testing. And here I have a picture of the famous iron Byron, which is used to test a golf club. The question arises, why don't we do this for hockey? Well, the fact is that with hockey, you have to hold the stick in 2 locations, and the stick needs to be able to bend through a very large angle between those 2 locations. So we eventually came up with what we thought was a winning design. Here's a MapleSim model of our hockey robot. We call him Thor, as in the hockey robot. And here is our actual prototype, which will now take a slap shot at well over 100 miles per hour. So I see that I only have a couple of minutes left. Let me move on to the last topic, which is hybrid electric vehicle modeling. And in this particular case, we're using models to improve the design of the hybrid electric vehicles, but we're also using models to tune the controllers for these vehicles. In this particular case, we're looking at a power split hybrid. This is a representation of the topology of the system. The green ellipses represent components that are already represented within MapleSim's built-in library of components. The orange ellipses represent simple control signals that are easy to add to a MapleSim model. The red ellipses are the ones I want to focus on here. These are the ones that we've modeled using custom components at the equation level. So for example, for a lithium-ion battery, we've used porous electrode battery theory, in which we represent the changing concentrations of lithium ions from anode to cathode. Those are represented as partial differential equations within our custom component template, which we then solve within MapleSim to simulate the response of the battery. And comparisons against discharge experiments and charging experiments show really good agreement. We've also created some fairly high-fidelity models of internal combustion engines, and that includes the throttle valve itself, the intake manifold, the combustion occurring in the engine cylinders, And finally, we've attached a dynamometer on here in order to subject the engine to different loads, again for validation purposes. These are all coded as custom components within MapleSim. We've even done some very high-level suspension modeling so that when we want to model a vehicle with a suspension such as a McPherson strut at the front, we can simply just drag and drop the suspension components between the tires and the chassis so that we can create vehicle models extremely quickly. And we've done the same with double wishbones as well as multi-links. Putting everything together, we can create a model of our power split hybrid electric vehicle, including batteries, motor generators, a power split device, which takes care of our transmission, and our internal combustion engine model. And with that, we can start doing detailed simulation results. On the top, we have a typical drive cycle, which is the speed of the vehicle versus time. And for that particular drive cycle down below, I've plotted the state of charge of the battery. And with this information, we can now design engine and vehicle controllers that will minimize fuel consumption and maximize the battery life. And with that, I thank you for attending today, and I look forward to handling your questions in the follow-up Q&A session.
So I'm here to talk to you about advanced physical modeling tackles the complexity of modern engineering. My name is Venkat Krovi, and I'm with the Mechanical and Aerospace Engineering Department at SUNY Buffalo. For those of you who are unaware, SUNY Buffalo, or University at Buffalo as it's known, is the flagship campus of the State University of New York system. And in there, I direct the automation, robotics, and mechatronics lab. For people who are interested in finding out more, I'd encourage you to visit the website that's shown here. I have a quick slide that showcases some of my research interests. My focus over the past 15 years has been on life cycle treatment of smart mechanical and mechatronic systems. And in particular, I'm very interested in the topic of modulation of physical power by articulated electromechanical systems. So the range of top of applications is sort of listed on the left, and you can see in the middle of the slide some of the different projects that we've worked on. And I think our focus in almost all of these has been going from concept all the way through to simulation and testing. And so there's a design, modeling, analysis, simulation, and prototyping stage that sort of formed the core of my research activities. Again, the details of a lot of these will be on the website in the form of papers, videos, etc. But I'll try to give you a quick snapshot of some of these in the next few slides. From a professional activities perspective, I'm relatively active in both the IEEE and the ASME, primarily in the robotics and mechatronics areas. In most recently, I guess I'll be serving as the General Conference Chair for the International Design Engineering Technical Conferences to be held in Buffalo in August 2014. So I'll perhaps look forward to seeing some of you there. In terms of what I'd like to talk about, there are many more topics than what I have listed here, but I wanted to share the following 4 with you. And my interest in all of these is not to delve too much into the research dimension as much as focus the discussion more on how MapleSim was able to sort of help us perform this research better, faster, more reliably. And so I'll focus the discussion on those topics. So to start off with, I wanted to discuss haptic steer-by-wire driving simulators, and in particular, the aspect of vehicle dynamics modeling. So this was work that was reported in the conference paper that's noted here, which is available from our website. But the core concept can be seen from this visual. In a haptic steer-by-wire simulator, you are removing the steering column that traditionally provides the feedback that comes from driving from the drive wheels back to the steering wheel, and you're now replacing it by an electronic connection. In doing so, some of the proprioceptive capabilities that come back through the physical connection of the steering column are lost and need to be replaced by an appropriate simulation. And in this case, a haptic simulation that involves both the visual dimension as well as the vibrotactile / force feedback dimensions. There are many factors that go to affect a haptic driving simulator, but a couple of the important ones are the fidelity of the haptic model, which is essentially a dynamic model of the vehicle, and the haptic user interface fidelity. In today's discussion, I want to focus on the haptic model and the role of MapleSim in helping us come up with an appropriate haptic model. But I think the broad challenge that I want to highlight here is I think that people should be well aware of is that as you're trying to perform this in real time at perhaps at high update rates of maybe up to 1,000 hertz, there are trade-offs between performance and stability of the system and the accuracy versus speed that often cause designers to make choices. These choices clearly simple models are better, whereas as you increase the model fidelity, your performance starts to degrade. And in particular, I think our concern here was in coming up with the correct set of models for some of these higher degree of freedom systems. So from this perspective, we chose to employ MapleSim to help us come up with some of these higher degree of freedom models. So what you're seeing in the slide is a 14 degree of freedom model, which consists of the 6 chassis degrees of freedom, and then you have the 4 suspension translation degrees of freedom and the 4 tire rotation degrees of freedom. And traditionally, as a spatial model, the equations of motion for a system like this can get very, very complicated. And being able to keep track of it correctly and being able to code it up correctly and simulate it can be quite a challenge. But I think our ability to use MapleSim allowed us to now use actually the same model, the full 14 degree of freedom model, and then be able to restrict it to become a 10 degree of freedom model and some of these lower fidelity models, and take it through the build, generate equations of motion, and finally implement as a block within MATLAB and Simulink. So we were able to use this now with other tool chains to come up with the real-time simulations. This ability to transparently change the fidelity of the model became very useful as we were trying to study the effect of different modeling fidelities on user performance. So what you're seeing here is a simple test setup where a user was using a Microsoft steering wheel, or in this case, an Omni type device to create different types of haptic feedback for driving along different types of trajectories. So moving along, I wanted to transition into some other work we've been doing with respect to parallel manipulators, and especially in the context of haptic teleoperation with these parallel manipulators. Our focus in the next slide that you're going to see here is bilateral teleoperation between a master device that I'm holding with my hand and a slave device that is now moving, that you see moving in the middle of your screen. Both these devices happen to be parallel architecture devices, and our interest in making both the master and slave device parallel architecture was to enhance some of the performance capabilities of these systems, including things like stiffness, stability, payload capacity, and so on. The model-based teleoperation, which is the paradigm that we were employing, unfortunately requires an accurate model. And coming up with models of these systems for both the handheld master or the remote slave, which have these complex kinematic chains, can be quite tedious. And so we again chose to use the MapleSim route to come up with models of these different devices within MapleSim, and we did a few different things. We were able to sort of initially visualize a lot of them directly within MapleSim, as you see on the extreme top right of your screens. What we were also able to do was extract the equations of motion symbolically that we were going to use for our model-based control. But as an interim step, we were able to export these directly to MATLAB and be able to simulate that system within MATLAB. And so as you will see in the next slide here, we are able to perform comparative analyses between the MapleSim model that you see on the top left with the MATLAB model that you see on the bottom left. And in addition, we were also able to simulate this under a variety of circumstances, with gravity, without gravity, to be able to sort of develop confidence in these models. We had the ability to also transform these models into different formulations. Some of our model-based work required the minimal formulation, in which case we were able to use just 16 degrees of 16 generalized coordinates with 10 constraints. And in other cases, we wanted to model this in the full extended formulation, so with 24 generalized coordinates and 18 constraints. Transitioning between formulations of this sort in the traditional setting would have posed would have taken a long time to realize. In this case, I think we were able to do this sort of relatively easily using MapleSim, and so that remains one of those positive features that we were able to exploit. So moving on, I wanted to also say we use this process with both the slave device that you saw in the earlier slides, but also the master haptic device. But I won't delve into the details here. There are papers, videos, etc. on my website that have more details. So I want to switch gears a little bit here. I wanted to talk a little bit about how we were using MapleSim in the context of mechanisms and robotics education. What we found was, as we were training our research students in the research process, we also saw a need to infuse MapleSim into the education process during the process of training them. And so some of the work we performed was actually reported in a conference paper and then in a journal paper where it actually won the Best Journal Paper Award. So the core challenge that we saw was that in the traditional approach, we emphasize a lot of sort of hand calculations. So shown here in the picture is the development of the Lagrangian formulation for a double pendulum, for example. And this process is emphasized in a didactic form, and then homeworks are assigned with this. But we find that when we start to look at systems such as the closed loop parallel manipulators that you saw earlier, a hand coding approach cannot scale up very easily, and so there was a need to sort of transition through to the automated approach using MapleSim. But the challenge that we saw was that students were not familiar with the theory and formulations, nor were they familiar with the tools, and so this was a gap that we needed to sort of fill in, and so we developed a set of self-paced tutorials to sort of help our students make this transition. And so we started out with relatively simple examples. So the first level of examples were things like the pendulum, and the idea was to get the students familiarized with the tools, and then we would transition it into slightly more complicated mechanisms such as the double pendulum or the 4-bar. And as a final project for their course, we would actually have them look at planar parallel mechanisms, as I'll show you in the next few slides. So there was a staged process where we wanted to get them to develop basic competency grounded in sort of their earlier experiences, understanding how simple pendulum and other things work. And then once they were more familiar with these tools, they were able to apply them to some of these more complicated problems. So in the phase 1, for example, you see here is the simple pendulum example. In a system like this, perhaps hand coding it, developing the equations by hand and then hand coding it probably would have been a simpler solution. But we were using this as a way to get the students to gain some insights into the modeling process. We were able to have them do simple benchmark tests such as what is the swing frequency of a pendulum such as this, or how much torque would it require for operating such a simple pendulum, and then transitioning it into slightly more complicated examples such as the 4-bar that you see moving in this slide, gave them further insights into the power of this tool. So again, in this case, rather than keep things limited to simple simulations, we were able to have them perform things like static and dynamic balancing of these 4-bars, which now, because they had access to the symbolic equations, they could actually see the cause-effect relationships relatively easily. And by the time they came to their final projects, they were examining planar parallel manipulators of the sort that are shown here. So shown on the top left here is a 3RRR planar parallel manipulator, and shown in the bottom left here is the 3PRR planar parallel manipulator. And the students could now explore choices such as location of actuation, changes in generalized coordinates, change in some of the physical dimensions of the system and its effect on performance of the system. So I think this slide kind of illustrates why we felt that this approach becomes useful. So what you're seeing here is now the mass matrix for the planar parallel manipulator. And as you can see from the complexity of the terms involved, doing something like this would just not have been possible within the scope of a one semester course if we didn't have tools such as MapleSim. But using MapleSim, we could now start to explore concepts such as sensitivity analysis, being able to examine roles of changing selected parameters such as the mass or of one particular link length, and be able to examine its effect on the composite system performance. So in sort of summary, as I've gone through some of these different slides, I hope I've given you a flavor of how we've used MapleSim as a convenient tool to help to come up with these equations of motion of relatively complicated articulated electromechanical systems. And I would invite you to visit my lab's website for further details on any one of these. And I hope to continue this discussion with you at some later time.
Today, I'm going to limit my presentations to two applications and projects that we use, the Maple and MapleSim, and one of them is on a space application in rover modeling, which somehow complement what John mentioned about the modeling of rovers. The other one is in parallel robot applications. In rovers, as John mentioned, that's the future of space explorations. In modeling these rovers, obviously, what we need to do is to develop a platform to allow us to easily model them, and if needed, to do some hardware-in-the-loop analysis. So what we did in this project was to develop a special library, a dedicated library for rover modeling. So if you look at the rover, it's made of, obviously, the overall rover dynamics that we need to somehow capture. It also has wheels that generate the contact between the rover and the ground. And also we need to somehow model the solar cells, wheel motors, battery, power electronics, heaters, and rovers, robotic arms, and other devices that we have in any rover. And the other thing is to be able to somehow add and introduce the terrain. And finally, the environment, and that is the location of the sun, the amount of energy that the solar panels can receive. And what we did, we developed, as I said, a platform that allows us to design and to study any of these rovers relatively easy. Now, here is an example. On the top right side, you see a rover, which is based on a bogie rocker structure, which is very common in rover design. And if you look at the Maple model on the left-hand side, you see the yellow component, which is the rover model, rover body. And that rover is connected to two revolute joints on the left and the right-hand side. And on the top, we have added a constraint, and that constraint is generating a differential motion between the left and the right revolute joint. That differential is mostly to make the rotation and the orientation of the body less dependent on the position of the wheels. And if you follow again this, the right-hand side revolute joint is connected to the yellow arm, the blue arm, and the blue arm, as you see on the picture on the right-hand side, is connected to one revolute joint on the top, and through that is connected to the wheel. And that revolute joint is introduced for the steering mechanism of the rover. And then from the bottom side is connected to another revolute joint that is connected to the yellow or the rocker arm. The rocker arm from the top is connected to a wheel that does not have any steering mechanism, but from the bottom is connected to another revolute joint that is its axis is normal to the ground, and that is, again, for the steering of the wheel. So we have the same thing on the left-hand side. Now, if we want to simulate and analyze this, we have added a steering mechanism or a steering command right in the middle. From the bottom part, we are applying the angular velocity input, and from the left-hand side, we are applying the steering angular inputs. By the combination of these two, we can easily simulate and animate the rover motion. So if you look at the overall platform that is now all in MapleSim, we have a component library that it has many built-in MapleSim components, plus those components that we have developed specifically for rover analysis. And on the right-hand side, it shows exactly how the rover, the structure of the rover, is very similar to what at the end the MapleSim model will look like. Now here it shows the animation that been done in MapleSim, and you see how the train has been introduced and how the rover can move and negotiate very easily with the train. Now, the other aspect of this project was to be able to do hardware-in-the-loop analysis. So what we did, we developed a test platform that has lighting system, solar arrays that you can see on the right-hand side. It also has a battery, motor, and flywheel. The flywheel is obviously to somehow represent the inertia of the rover, and the battery and the motor for the source and the motion of the rover. And then what we did, we added extra components, and those extra components, as you see on the left-hand side, they are for the solar panel, the battery that is built into MapleSim. It also has components for irradiation, for the winter environment, or any other component that is needed for the rover platform. And on the right-hand side, you see the rover itself, plus the solar panel, battery, and also the 6 motors that are connected, plus on the left-hand side, that's the environment. And the environment provides the train data, plus the location of the sun, the amount of energy it can receive based on the orientation of the solar panel. And then once that is done, then that can be transferred into, in our case, into Natural Instrument device. So if you look at this diagram, on the left-hand side, we have all the inputs, including the path planning, rover kinematics, and all other things. The software structure, which is based on MapleSim, and once the model is developed, we transfer that into LabVIEW, that is done automatically. And then in LabVIEW, through a PXI or any LabVIEW real-time structure, we can start doing hardware-in-the-loop analysis. The hardware-in-the-loop analysis means that we can have some hardware component, the rest software. So if you look at on the right-hand side, the hardware, the test bench, we can have, for example, the lighting in the form of hardware or software. We can switch some of these components from the software to the hardware side or vice versa. And then based on that, we should be able to look at the performance of the model, the validity, or to validate the model, and also the performance of the hardware components. And once it's in LabVIEW, then obviously you can add your own GUI and user interface to monitor all the variables. And here it shows the result of the hardware and the simulation. The black line is showing the state of the charge of the battery using pure hardware and also hardware in the loop. They are following each other very nicely. There are some discrepancies that is obviously between the experiment and software. You expect them. And the blue and the red lines showing the power generated and the power consumed. The power consumed is because of the movement of the rover, and the power generated is because of the energy received by the solar panels. In the robotic applications, what we have done was to look at conventional delta parallel robots, And what we have done is to replace those rigid elements of Delta robot with cables that you can see in the middle side. By replacing the rigid component with cables, what you need to do is to keep all the cables in tension all the time. And because of that, we have replaced, or we have added, a passive pneumatic cylinder right in the middle. And that pneumatic cylinder is keeping all the cables in tension. Now, when it comes to the design and optimization, there are many factors that you need to look at in order to optimize the overall system. Now, those are the geometrical dimensions of the robot, and also the type and the size of the motors. So by defining an objective function that in our case was using off-the-shelf motors with the torque and the speed characteristic, and also trying to minimum the torque that is applied to the motor, and also keeping or considering the maximum speed that we are expecting from this robot, then we develop a Maple model of this in order to do an optimization. Now, the first thing that we did was to model the cables in MapleSim. And by modeling the cables, which was based on a rigid arm plus a spring, and also the spring stiffness was not linear, was a nonlinear form, and based on that, we managed to put together the overall model of the parallel robot. Now, this is the overall robot after the optimization, and the optimization was, again, as I said, was mostly on the overall dimension and the minimum pressure in the main cylinder in the middle, and we prototyped it, and here you can see the MapleSim animation slide, which shows on the right-hand side for what type of inputs we would like to animate the system. And here I have two animation of the robot that you see. The left-hand side is showing all the arms are moving, and on the right-hand side, one of the arm is stationary and the other two arms are moving. So based on this approach, it was very easy to put together the overall equations, add all the constraints related to cables, and based on that, be able to optimize the overall system.
That concludes this session. Thank you for joining us today. Don't forget to visit the Communication Lounge to ask any questions you may have. A recorded version of this presentation will be archived, and you will be notified when it's available.